So before I really dive in, I want to pass this black box around. This is a spectrometer. And I want you, as you're able, to look at the different lights I have up here. And I'm going to talk about this later, but and if you can't see it well from back there, that's fine. You can come up afterwards and stick it up close to the light. Basically, look through it. There's a slit right here. Then off to the side, you'll see its spectrum. And this will be relevant in a few minutes. So go ahead and just pass that along. So by way of review, the first week we talked about how God tends to use middlemen in the accomplishment of his creative acts in the cosmos. We showed that God of the gaps is usually bad theology when you apply it to the created order, and we talked about how this relates to the pi model of creation as opposed to what I proposed, actually I stole it from another guy, is the layered cake model. And we're told in Scripture to do science. One of the reasons we're told to do science is that it enhances our worship of God. In the second week, we talked about the different creation models that have been prevalent in the church for 2,000 years. And those tend to be young earth creationism, old earth creationism, intelligent design, and theistic evolution. Then the third week, in which I was gone, but presented a video, so thanks for suffering through that, I gave my personal science faith testimony about how I find theistic evolution to be a biblically and scientifically satisfying model for explaining both what we observe in nature and how we understand how God works in the created order as revealed in Scripture. So my presentation for today, and the presentation, feel free to just interrupt and talk over me, that's fine. It's a combination of talking about three big things, kind of Big Bang cosmology, the cosmos as something that's really big, and also on the geology side of things, radiometric age dating, how we understand how old rocks are on Earth. And I'm going to be jumping back and forth, unfortunately, a little bit between kind of like academic classroom explanations. Dee, it might work better if you hold it sideways. There you go. Yeah. So kind of jumping back and forth between like academic science classroom stuff versus like really cool stuff on the screen. So I want to get started with talking about the Big Bang, where everything came from. So I'm sure most people have heard of the Big Bang, not just the TV show, which is excellent, by the way, but Big Bang cosmology. So, the Big Bang theory states that the cosmos came into being, and it doesn't say how it came into being, it just says that it came into being about 13.8 billion years ago. Now, when I was growing up in high school, that number was only constrained to between 10 and 20 billion years. Then I remember when that was refined down to about 15 billion years, and then 14, and then people really started zeroing in on 13.8 billion years. Last I checked, it was 13.79 billion years.
So Kirby, how did they come about with that number? How are they narrowing it down?
So it's from a combination of things, looking at the expansion of the cosmos, which I'm going to talk about a little bit, also different the ages of really small stars. The smaller a star is, the longer it lives. It's kind of counterintuitive. The really large stars burn out fast and die young. And so it's a combination of looking at that, looking at the isotopic ratios in those stars, and you have multiple lines of converging evidence that are actually used to constrain each other, and where they all overlap gives you a very narrow window of confidence in how old the universe is. So the Big Bang theory is largely based on the observation that galaxy clusters are all moving away from each other. And with the spectrometer that I'm passing around, as you look at the different light sources, there's 3 fluorescent lights, and there's 1 incandescent light. The 3 fluorescent lights will show you what are called emission lines in the spectrum. Were you able to see those different lines? Every single element has its own unique set of emission lines in its spectrum. As you break its light into a rainbow, it's not a continuous rainbow, with the exception of the incandescent bulb, which is a type of radiation called black body radiation, and this is like excited fluorescence. If these light sources were moving away from you very quickly, you would still see those same lines, but they'd all be shifted toward the red end of the spectrum. So I think, yes, okay. So here they are unshifted. As they're moving away from you, you would see them shifted toward the red. If they were coming toward you, they'd be all shifted towards the blue. And so these observations were made really starting in the late 1920s by Edwin Hubble. an American astronomer who liked to fake a British accent a lot. He was eccentric. And so he made these observations, published a paper in 1929, and another paper in, I think, 1931 or so, showing his observations, many of which are plotted here, where the further away you look, the more something gets redshifted. And so it was a lot of these observations that started to show, hey, the universe is expanding. That observation was coupled with observations starting in the late 1980s of what's called the cosmic microwave background radiation. And this is what clinched it for most astrophysicists that the Big Bang model was the correct model for the initial evolution of the universe. The cosmic microwave background radiation was predicted to have existed before it was discovered. Actually, it was discovered in the 1960s, but then we were able to make much finer measurements from the 80s onward to the present. That is, you can think of it as fossilized light from the Big Bang. The initial light from the first stars that turned on got redshifted from the expansion of the universe all the way into the microwave part of the spectrum. Microwaves fall right between infrared and radio waves. And so these are light waves that have been stretched literally by the expansion of the cosmos to do that. Now, between the discovery of the CMB, the cosmic microwave background, and the discovery that the cosmos is expanding, most, or the establishment of astrophysicists tended to accept a different model for the universe, namely the steady state model, that the universe was infinitely old, which therefore didn't require a creator in their worldview. And they reconciled its expansion with the notion that, well, okay, so the universe is constantly expanding, but the reason nothing is infinitely far away is because new matter gets created to fill the void. And as crazy as that sounds, that's actually not disallowed by the laws of physics. So that was kind of their fudge factor, until this was discovered, I think 1960, by Bell Lab physicist Arnold Penzias and his buddies. And the problem with the steady state model is that that is not predicted, but it is predicted from the Big Bang model. Now, the Big Bang is typically portrayed as a large explosion at the beginning of the universe, and that's really kind of an unfortunate way to describe it. The Big Bang was not an explosion the way we would think of it. It wasn't as if God tossed a grenade into a vacuum and it just went boom. So by not an ordinary explosion, what I mean is that there was literally no, it was both matter and energy, that explosion, but it was also the simultaneous creation and expansion of the three spatial dimensions, length, width, and height, and the fourth dimension of time. So literally, the cosmos expanded into the space that it created. It would be analogous to having like a rubber whiteboard, like coloring it all in, and be like, oh, but I want a bigger picture. Okay, so I'll just stretch the whiteboard. And then you can't draw a bigger picture. And so the cosmos, it wasn't an explosion. It literally created the space that it expanded into. It was also it also created the time that went by as it expanded. Since it created its own time, it's an undefined quantity to ask what happened before the Big Bang. That literally does not make sense, at least from our perspective inside the universe. It's sort of like asking what's north of the North Pole. You go there and it's like, all right, where do I go from here? Up? No. Yeah. So conceptually, that's kind of what the Big Bang is. So it's not an explosion. That's really a bad analogy. In fact, the Big Bang was a pejorative term coined by, I'm blanking on the astrophysicist's name, who didn't like it. He proposed the steady state theory. He liked the steady state theory. What's that?
Oil?
It may have been Fred Hoyle. And the Big Bang was termed pejoratively. It's like, oh, these astronomers just think this big bang happens and out off the universe, but the name stuck. What else do I want to say? So there's also no center to the expansion. If the universe is creating the spatial and temporal dimensions that the matter is expanding to fill, that means that there's no center to the explosion. Every other point is moving away from every other point. And I wish I had brought a balloon, but a great analogy that's often used is to take a balloon, draw little dots on it to represent stars and galaxies, and then to blow up the balloon and show that every point is moving away from every other point. But there's no center to that expansion. The inside of the balloon is not considered here. All we're talking about is that two-dimensional surface of the balloon representing the three-dimensional surface of space-time. And as this expands, everything moves away, but there's no center to the expansion. So if I blew your mind, I can kind of deflate your mind if you do the balloon experiment and just scale it up in your head from 2 dimensions to 3.
Can I ask
Yes.
a dumb question?
Not a dumb question, but yes.
So I have always heard with respect to the Big Bang that singularity
Mm-hmm.
and then expansion.
Yeah.
So what was singularity then? I mean, that's not the center, I understand what you're saying.
Right.
Is that's the point from which the expansion started, or?
Basically, yes. The problem with singularities is that in mathematics, which isn't allowed, and so we can only talk about the universe up until 10 to the minus 40th seconds after it started to exist, which is a tiny, ridiculously small amount of time. But by singularity, it's kind of an abstraction.
Okay.
It's kind of an abstraction.
With everything moving away from everything else, are all the planets in our solar system moving away from us?
No, so this is only on the very large scale. So this is with regard to galaxy clusters, which means I have to start getting into my pictures now. So
We're stable, but our cluster is...
right. So you have clusters of galaxies that are all gravitationally bound to each other, and they're all moving away from every other galaxy cluster because the space between them is expanding. In a sense, the Big Bang never stopped banging. It's still banging, and it's the constant expansion of space-time. So really, the Big Bang it's where you started with, I'm going to contradict myself, before the Big Bang there was nothing, there wasn't even nothingness, there was no vacuum, there wasn't even spatial dimensions, there was no time, so maybe from God's perspective. Before there was nothing, and then all of a sudden there was an expanding universe. You go instantaneously from nothing to an expanding universe. And it's still expanding. So we're still in the Big Bang in that sense.
So what scientists say, where did it come from?
So if you look at what science is, that question is actually, it's a great question to ask scientifically. But by definition of the universe, you can't ask what's outside the universe from a testable or an observational perspective. There's no experiment you can do, there's no observation you can make to see what's outside the universe. And so I believe the answer to that question lies squarely in the realm of religion and philosophy. And Pope John Paul II agreed with me. So now you get hypotheses like, well, instead of positing an infinite life form, we'll just call it God, let's posit the multiverse, where you have a realm where lots of baby universes are going off all the time. Lots of big bangs going on, but they're all separate universes. That's a great story, bro, but that's not a testable. It's not a testable hypothesis. So it kind of stays in the realm of philosophy. You can believe that, but it's
Stephen
not
Hawking,
scientific.
what does he say? Where does it? Does he just not have an explanation?
He likes to kind of keep that to himself, I think. Stephen Hawking. That's good.
But so scientists are saying since we can't even think about it, then who cares?
No, it's not who cares. It's we very much want to know.
Right, but you're saying since we can't.
But it's it's probably not a scientific question, unfortunately.
Okay, right. So from a scientific point of view, it's like since it's not a scientific question, then we just won't even think about it.
Well, scientists are also humans, and they bring their philosophical biases to things, and so we want to know. It's just
I know.
It's unsatisfying.
But isn't that a big black hole for the science guys?
In that sense, a black hole, yeah. It's just unsatisfying from a scientific perspective. Yeah.
Right. You indicate that the gap inside the galaxies is this expansion continuing expansion inside the galaxy. Is that where the birth of the stars come in? Is that in the galaxy or is that outside?
This tells me I need to get on with my PowerPoint slide. So, I'm going to come back to this, I think. All right, here's a galaxy cluster. Since we're talking about galaxy clusters, I'll just show you one. Here's a whole bunch of elliptical galaxies. There's some smaller galaxies spread out through here. If you look closely, you can see these arcs, which are the distorted images of background galaxies, and their light is being warped by the gravity from this foreground galaxy cluster. It is literally a lens made out of gravity. It's called a gravitational lens. And what's interesting is that it magnifies and enhances the images from background galaxies that we wouldn't otherwise be able to see. And it's the space between these galaxy clusters that's expanding. Now, it's hypothesized that far into the future, like hundreds of billions of years, that the space within galaxy clusters will start expanding. And then at some point, the space within galaxies will start expanding. At some point, the space between solar systems will start expanding. And at some point, the space between electrons and the nucleus of atoms will start expanding. And everything just flies apart at that point, completely. But that's like several hundred trillion years off. Don't worry about it.
Not in my
If
lifetime.
the Lord tarries, that's what will happen. So here's two gravitationally interacting galaxies. These are two galaxies that are orbiting each other, and you'll notice that these are two spiral galaxies. They've got these arms. They're spiral density waves of material where the stars are actually compressed. It's kind of like a star traffic jam. All the stars are orbiting in the middle, but they'll kind of clump up right here. But they clump up in just the right way so as to make the appearance of a spiral. Because if you're in a helicopter looking at Beltway at rush hour, you'd see these traffic patterns. Just cars between the bunched up places, but you really notice where it's bunched up. These two galaxies are interacting gravitationally, and people have done computer simulations of that, where this is a computer simulation of two galaxies orbiting each other. This happens on 100 million year time scales, and they're going to pause it and show actual images of galaxies in those approximate positions. And as these galaxies continue to orbit, they partially merge. Now the interesting thing is, as they merge, there's so much space between the stars that individual stars don't collide. But they can still feel each other gravitationally. And we see this sort of thing happening as we turn our telescopes to different places in the sky. As they continue to orbit each other, the gravity, it's just like tides. Instead of the moon pulling ocean water, it's the gravity of each galaxy pulling streams of stars in different patterns. And let's see, where's this going to end? So astronomers call those tidal tails. They're tides of stellar tails being pulled apart. And they're very pretty. So you were asking about the formation of stars. The formation of stars tends to happen in the spiral arms. We're looking at part of a spiral galaxy here, where the nucleus is here. As the stars orbit the center of the galaxy, and they tend to clump up here in the arms, in these spiral density waves, you get clouds of hydrogen gas, which you can see here in the pink. And those clouds of gas start compressing because of everything's getting compressed in these regions, and you end up with some clumpiness. And that clumpiness has an enhanced gravitational field because you've got more matter packed into a smaller space. And so that creates this runaway collapse of local hydrogen, such that you end up with a big ball of hydrogen that can start undergoing thermonuclear fusion in its core and create a star. And so what you see are all the blue stars you see are these really young, hot stars that have just formed from the collapse of hydrogen in the arms of these galaxies. So star formation has been going on for since the beginning of the universe. It's going to continue on for another several tens of billions of years, it's modeled. So that's where stars get formed. And again, the space that's expanding is the large-scale structure space between the clusters of galaxies.
The stars being formed is just by the compression of that gas.
That's right.
So, do they become matter, or they just stay gas?
Well, no. So it stays gas. Gas is a phase of matter, and as you get more and more gas, it wants to form a sphere so that every part has an equal gravitational attraction to every other part. As you move down towards the center of that, the pressure and temperature get so hot that you start fusing those hydrogen atoms together and making helium. So this is spiral galaxy NGC 1300, and it's probably a good approximation of what our galaxy would look like if we could get out of our own galaxy. But we're stuck in the middle of our galaxy, so it's hard to see. But this is a good idea of what it looks like. Notably is this kind of this straight bar that goes across. This is called a barred spiral galaxy. We also probably live in a barred spiral galaxy. And this is probably some funkiness going on with that spiral density wave of compression.
Is this a photograph or is this a representation?
No, this is a photograph from the Hubble Space Telescope of an actual galaxy. If your eyes were 2.4 meters across, this is what you would see. This is a picture of our galaxy from embedded inside of it in a national park somewhere. And
Australia.
or Australia.
Australia.
Thank you.
Here's rock.
Wow, I'm impressed. What is it? Ayers Rock? Okay. So the idea that we live in a spiral galaxy comes from, I don't know if I have it. Okay, here we're looking at a spiral galaxy, kind of edge on. There's the nucleus. And we kind of have the same view of our own galaxy, where here's the galactic center, the bulge, and then we're inside this disk of stars looking out. And so we see this plane of stars. And on a really dark night, you can kind of see that. Not around here, though, unfortunately. And it tends to be more in the summer. Here's an edge-on galaxy. This is, this is NGC 4013. This is a photograph from the Hubble Space Telescope. This star is probably a foreground star in our own galaxy that's just kind of in the way. And so we're looking at the galaxy behind it as this plane of stars and dust in the plane of that. More galaxy clusters. So this one has a lot of gravitational lensing around it. Just a few days ago, there was a report that astronomers saw, one of the cool things where I'm going with this, with the gravitational lensing, is that you can get multiple images of the same galaxy. You can see the same galaxy smeared out in different positions in different parts of the image there. And just a few weeks ago, some astrophysicists saw a supernova go off in one of those images of a galaxy. And then they predicted, of course, that since we see multiple images of that later on, we should see that supernova appear in those other images. And they predicted how long that should be because the path length for the light to take is different for each of those images, so it's a slightly different travel time. And they were right in predicting when they would see the supernova in those other images of that same galaxy, and they saw it. So that's pretty cool. Okay, large-scale structure of the universe. If you could zoom out, you would see a web. The universe is like a giant sponge with these tendrils of galaxy clusters coming together, with huge void spaces in between. And it's that void space, these bubbles in here, that are where the large-scale expansion of the universe is really happening. And these are computer models of, based on the mapping that's gone on for the distances. This is what we suspect. Here's a computer model of what the cosmos would have looked like when it was only 900 million years old. When the cosmos was then 3.2 billion years old, it started to take on some of this web structure. And after gravity, and both expansion and gravity working together have gone on long enough to the present, 13.8 billion years, we really started to get this well-defined web structure of galactic clusters. Okay.
So it's expanding, you think it's finite at the moment, but yet it'll go on, it'll expand with time.
Probably.
So I mean, it's not like the universe is infinite at this moment, right?
That's probably right. My latest understanding is that, so the cosmos, while enormous, is still finite in volume. However, if you could go off traveling in one direction fast enough, eventually you'd come back to where you started. Because it's, as far as we can tell, the cosmos loops back around on itself. It's sort of like if you ever played classic Mario Brothers, and you go off the right side of the screen and come back on the left. So I've been talking about all these crazy distances, but how do we know how big these distances are? They're not just gut feelings. What we have, and I'm sorry for jumping around so much, it was hard to tell what order I should present things in. So we have multiple overlapping techniques. We got to turn the lights back on for the kiddos. They're coming in around the line. Have the lights affect both sides of the tree. Okay. Okay, so what we have here are distances along here, and then each bar represents a different technique for figuring out how far away stuff is. What's not on here would be over here, how we tell how far away things are in our own solar system, and we can use radar for that. We can use large radio telescopes like the Arecibo Observatory. We can use dishes from NASA's Deep Space Network to literally ping other planets. We've been able to do radar imaging of the north and south pole of the planet Mercury. For this, we can image passing asteroids using this. We can tell how far away Mars is using this. So that's good for like our solar system. For stars outside our solar system, but in our neck of the woods of the galaxy, the next thing we can do is called parallax. where you take an image of the position of a star, you wait 6 months until Earth is on the other side of its orbit, and then you image the same field again. And the closer stars will appear to have shifted back and forth a little bit between relative to the further away star. Just like holding out your finger, closing one eye and then the other one, you can see your finger shifting relative to the background. And it's basically simple trigonometry at that point. I think it's the arc cosine of half the angle will give you how far away it is, because you know the size of Earth's orbit, and you know what angle that star appeared to move in the sky, and so you can calculate just from trigonometry how far away that star is. That's good out to about 300 light years. By the way, a light year is 5.9 trillion miles. People use it. People use it to mean a length of time. It's not. It's a length of distance. It's how far light travels in 1 year. That's all it is. Turn on a flashlight. Turn it off. In a year, it's a light year away. That beam is light. So parallax is good from right up close to about 300 light years away. Further than that, we need something else. Fortunately, there's a method called spectroscopic parallax, which is just basically looking at how bright a star is and how bright it would be if it were closer. And you can calculate how close it would be. And there's a good bit of overlap between that and parallax, so we can really calibrate it pretty well and have a good understanding of that. As we get further away, so by the way, so around 300 light years, that's like 0.3% of the distance across our galaxy. So that's still like really close. Our galaxy is 100,000 light years across. The closest large galaxy is 2.2 million light years away. You know. So we're talking
A lot of zeros.
A lot of zeros. Moving further away, so now we're out to about 30,000 light years. That's about 3 times the thickness of the disk of our galaxy, and that's about 1/3 of the way. So 30,000 light years is how far we are from the edge of our galaxy, basically. And so for those distances, we can use various populations of variable stars. And these are stars that you can watch how they vary in brightness over certain periods of time. And physicists have worked out a relationship between how fast it's pulsating and how bright it actually would be. And so based on how fast it's pulsating, you can deduce how bright it actually is, compare that with how bright it looks, and you can figure out its distance. And fortunately, that overlaps with the spectroscopic parallax so that we can calibrate it, which in turn is calibrated based on parallax. Moving even further away, so population 1 Cepheid variables. These are good for looking at galaxies out to 30 million light years. So that includes a good number of galaxies, including the Andromeda galaxy, which is the largest close galaxy to Earth, 2.2 million light years away. And so that's a fairly good measurement of how far away these objects are. Then overlapping with the type population 1 Cepheid variables, you can use type 1a supernovae to figure out how far away things are. Again, based on how bright it looks versus how bright it has to be, and deducing its distance. Now, type 1a supernovae, I'm not sure if I have more slides on that or not, are crazy. You have a burned out white dwarf hulk of a star orbiting another star, and this tiny burned out white dwarf star is about the size of Earth. It's tiny, but it's gravitationally siphoning hydrogen from this other star onto its surface until it builds up enough pressure to have the core of that collapse and then rebound in an enormous explosion. And the physics of this are such that it has to be the same brightness every single time. Every type 1a supernova is essentially identical to every other type 1a supernova. Because they're all identical, astronomers use the term standard candle to say, all right, well, we know all type 1a supernovae are really the same intrinsic brightness, so we'll use how bright it actually looks to figure out how far away it is. And it's by studying these type 1a supernovae in the late 1990s that a group of astrophysicists showed that the expansion of the universe is actually speeding up. By measuring the distances to type 1a supernovae at different distances, they were able to see, wow, the universe is actually speeding up in its expansion, which nobody predicted. So it's a big surprise. I wasn't planning on talking about that, but just kind of fell. Any questions on
You know, all this light that we're seeing is from billions of years ago.
Yes.
So is there any theory like, well, actually there's nothing, at some point there's nothing there? Like we're looking at
Something that's sort of
30 billion years ago, and maybe not in today's terms, it's all gone.
Right. So yes, you're absolutely correct, and that's worth emphasizing that as we look further away, we are literally, not figuratively, we are literally looking backwards in time. We are looking at something that happened a long time ago. It's like watching fireworks going off, seeing it, but then the speed of sound is much slower than light, and only hearing it later. When you hear a firework explosion, you're hearing something that happened back in time by a second or two in this case. But with light, because of its finite travel speed, you're literally looking into the past. And so whatever we're seeing isn't what it looks like anymore. There's no way to see what it looks like right now. We can model it, we can predict what it might look like. But a lot of stars that we see probably aren't there anymore. Whenever we see a supernova going off, that actually happened a long time ago, but we're only seeing the light from it now. So when we see, or for instance, like a Cepheid variable star pulsating in like the Andromeda galaxy, which is close by, and if a supernova went off in Andromeda, well, it might be bad news. It's a lot of radiation, and even it would be a lot of X-ray radiation hitting Earth's atmosphere to be bad.
Well, how long would it take to get here?
Well, 2 million years.
Okay.
Yeah.
So we're fine.
So the light you see, yeah, but by the time you see it, it's too late.
Yeah.
It's like by the time you hear the bullets already hit you.
Right.
Now, is there light that just goes off, disappears?
So yes, so you're talking about what's called the Hubble horizon. And that is light that hasn't had time to traverse the distance of the universe since the universe formed. So 13.8 billion years just ain't long enough for this photon of light to get to where it needs to go the other side of the universe. And so if the universe is, like this, every individual observer in the universe will have their own Hubble horizon. And that is, the radius of that is the distance that light has traveled in 13.8 billion years since the universe started.
So you could never look back and see the Big Bang?
This is getting very tricky. Possibly, yes. You can see it when light first arose, which is actually not at the same time as the Big Bang. Because you had to have, the universe was opaque to light prior to, I think, 300,000 years after it was formed. But the Hubble horizon, as the universe ages, grows bigger and bigger for each observer. And for close, relatively close observers, eventually their Hubble horizons will overlap and you can be like level. There you are. So, so there's realms of the universe based on the finite speed of light and the finite age of the universe that we can't see. That we have no information of.
The light that you've been looking at for X amount of years, does it ever just disappear entirely?
So if like a star went supernova and exploded, yeah, it'd go away.
Okay,
Like,
so
stars
supernova
die.
just
Stars
dies
die.
and that blasts
Yeah.
out.
So,
Have we ever seen a star die?
all the time. And you've anticipated my next slide set. Thank you. Thanks, Dee. So that's our sun, taken in ultraviolet light. Can I get to your question in like a minute? So I'm going to show this video.
Yes.
This is the sun. So, okay. I mentioned that when galaxies merge, they're so big that individual stars don't collide. Galaxies are huge, and stars are tiny. The stars are also huge. And this tries to illustrate that. So we're starting with the size of our moon, showing the relative sizes of the planets. By the way, the planets are rotating the wrong direction here. Mars, Venus and Earth are about the same size. Neptune. So we're the size of that storm on Neptune. There's Saturn without its rings. So it's only a little bit smaller than Jupiter. And then the sun's pretty big. But the sun's actually pretty small. This is Sirius A is a star in the constellation Canis Major. Pollux is in Gemini. Arcturus is in the constellation Boötes, and it's a red giant. You can also see Aldebaran in the night sky. It looks red. Rigel is in Orion. I don't know where that one is, but it's big. But not as big as this one. There's a red supergiant.
Do they have like super giant?
Oh, wait for it. They're hypergiants. So theoretically, the largest possible star would be 100 times the mass of the sun. However, they've actually seen them up to 200 times the mass of the sun, 200 solar masses. And so physics has a little bit to catch up to explain that. So stars are big, but then they're small compared to the galaxy that they're in. So, all right. So small stars like the sun, and actually a lot of stars are much smaller than the sun. They're called red dwarfs. And red dwarfs have lifetimes many times the age of the universe. They can, and their lifetime is defined by how long they fuse hydrogen in their cores and turn that hydrogen into helium. And so based on nuclear physics calculations, which I'm not qualified to do, these stars will burn, fuse hydrogen into helium for about 40 billion years, some even longer. The smaller you get, the longer you burn. Our sun, a type G2 star, will burn for 10 billion years, and we're about halfway through there. Large stars, like up to, so Rigel is a large star, 21 times the mass of the sun, and it's this star in Orion. Here's Orion's belt, here's kind of his sheath, here's his shoulders, here's his kneecaps. Rigel's this star right here. That's 21 times the mass of our sun, and the larger you are, the bigger you fall, and so through a series of, and so these pictures here are pictures of supernova that happens when the star dies. So a star like Rigel will burn hydrogen, and by burn I don't mean like burn, I mean fuse. It'll fuse hydrogen for 7 million years. That's the total time, so that's really short. It's only 7 million years. Our sun will burn for 10 billion years. So 7 million years. When it's done fusing hydrogen, it will partially collapse. It'll heat up its core, which is now made of helium, even more. And that helium will start to fuse, which will form carbon. But the helium fusion will only last 500,000 years. The carbon fusion will last 600 years. It'll start fusing neon for 1 year. It'll fuse oxygen for 6 months. It'll burn silicon, which is like what rocks are made out of. It'll fuse silicon for a day, compared to 7 million years. It'll fuse silicon for a day. Then its core will collapse, which will take 0.2 seconds. The core will reach what's called nuclear density, which is how tightly packed protons and neutrons are to each other. It'll rebound at that point, creating a shock wave of material of both regular matter and neutrinos, if you know what those are. And that shock wave of matter and neutrinos will rush up to the surface of the star. It'll take a few hours, and it'll completely blow apart that whole star. And in fact, that compression wave is so intense that at first it completely destroys all these complex elements that it made, turning them back into hydrogen. And then it refuses them into heavier elements as that shock wave propagates out. And what we see that shock wave as are nebula. We see supernova remnants. This is the Crab Nebula, or M1, seen by the Hubble Space Telescope. And this is this expanding cloud of gas from the incredibly violent supernova explosion. This is called a Type 2 supernova. I mentioned a Type 1a supernova earlier. This is a Type 2 supernova. Type 2 supernova are cool, but they're not useful for measuring distances. Here's a really faint red ring that we're seeing as the shell expands away from an exploded star. This is the supernova remnant 1987A. It's called that because it was the first supernova seen in 1987. And what's cool about that is it's a kind of a case study in how a supernova works. It's been studied continuously since then, and we can actually see it grow in size and see this shock. What we're seeing here is a shock wave of superheated gas as a shock wave encounters hydrogen in the interstellar medium, and it heats up. And so we're seeing this shock wave propagate away from what was from that dead star. What's left in the middle can either be a white dwarf or a neutron star, or sometimes a black hole if it's massive enough. And that's really bizarre physics. So I mentioned that supernovas create, the universe started out as hydrogen and helium. That's it. And it's nuclear fusion that happens in the cores of stars, and also especially in supernova explosions, that creates everything else on the periodic table. So the universe started with hydrogen, helium, all these nuclear fusion reactions to supernovas create everything else, including the atoms in our bodies, which is amazing. The food we eat, the metal of this music stand was created in the chocolate of the supernova.
Is our periodic table the same throughout the universe?
Yeah, using that spectroscope, like spectroscopy, we can look out and see the same elements all throughout the universe.
So there's no weird stuff out
Oh, there's weird stuff, but it's like weird isotopes of an element that we have, like different number of neutrons, basically. So this is just a GIF of a supernova going off in the Whirlpool galaxy, and supernovas are so violent that they can shine with about the same brightness as their host galaxy for a few days. They put out as much energy as their galaxy does. A galaxy of 100 billion stars can be outshone by one supernova, which is incredible. And so this inspires me to get back to Scripture about the God who created all this incredible, mind-blowing stuff. For you make me glad by your deeds, Lord. People are giggling. I sing for joy at what your hands have done. How great are your works, Lord. How profound your thoughts. And then in Job 38, God's talking to Job, putting him in his place. And he says, can you bind the chains of the Pleiades, which is an open star cluster we can see from here? Can you loosen Orion's belt? Can you send forth constellations in their seasons? Or lead out the bear with its cubs? It's talking about Ursa Major, the constellation, the Big Dipper. Do you know the laws of the heavens? Can you set up God's dominion over the earth? And then David is moved again here. And I meant, what would the Psalms read if David knew the science we know? Praise the Lord. I will extol the Lord with all my heart, in the council of the upright and in the assembly. Great are the works of the Lord. They are pondered by all who delight in them. Glorious and majestic are his deeds, and his righteousness endures forever. And I've included a couple galaxy pictures here. This is a blow-up of the Black Eye Galaxy, which has these dark clouds of interstellar dust that obscures light from background stars, and it's very contrasty. Ansel Adams would have loved it. All right, are we good on astrophysics?
Okay.
Okay.
Got it.
Let's get on to geology now.
Except I've got one other observation.
Yeah.
As the universe expands at an increasing rate, over time we'll see nothing.
Yeah, you're absolutely right.
So rather than seeing back into the early origins of the universe, we'll actually see nothing.
So you're right. So what I was saying here would break down at that point. At some point, so nothing is allowed to travel faster than light except space-time itself. General relativity allows that space-time can actually expand faster than light. And so eventually, while our Hubble horizon is expanding, the expansion of the cosmos is speeding up, such that everything will move beyond our Hubble horizon, because eventually everything will be accelerated beyond the speed of light from every observer's perspective, and we'd see nothing. It'd be a very boring universe to live in. Yeah. Okay, yes?
I wanted to go to the service, but I just wanted to say that I'm not a science person at all, but it blows me away to think that God would submit to being in a room. I mean, the God who created this is just, I can't understand.
Jesus, God the Son, submitted to being made of supernova detritus. The elements made in supernovas is what the Son of God became. Yeah. And so I'm not trying to talk to scientists. This is for people who aren't scientists but are interested and who want to know God more through what has been made. So you're like the poster child for my class. Thank you. So if there's no more questions on the origins of everything, I'll move on to radiometric age dating, which is how we know how old things on Earth are. The only way we can tell how old pretty much anything is in absolute terms is through this method of looking at ratios of different isotopes of elements. All right, what do I mean by that? If something is radioactive, take your drugstore variety uranium, it's got so many protons and so many neutrons packed into its nucleus. I'll draw protons in dark blue and neutrons as open circles. And uranium has so many protons that it's unstable. The nucleus of the atom will kick out particles from time to time. Anyway, yeah. So, and they come out in very predictable ways. There's two types of radiation that are relevant here. There's one type of radiation where 2 protons and 2 neutrons will get kicked out of a uranium atom or another radioactive atom, and that's called an alpha particle. If you're astute, you'll also realize that this is the same thing as a nucleus of helium. So as uranium and other radioactive elements decay, they're giving off helium. As you reduce the number of protons, you change what element you are, and eventually uranium will turn into lead. It'll lose enough protons that it'll work its way down the periodic chart to lead, because the number of protons you have tells you what element you are. Hydrogen always has 1 proton, helium always has 2 protons, lithium always has 3 protons, etc. Carbon always has 6 protons. Another type of radiation is more my favorite. I'm just going to draw a representative nucleus here. It's called beta minus radiation, and it's where a neutron kicks out an electron that it just kind of invented. It just kind of kicks out this electron, and it turns into a proton. And so that way you can move up the periodic chart and become the next element above you. I think it can also happen the other way, where a proton will kick off an anti-electron and turn into a neutron, then you go backwards on the periodic chart. So this is the craziness of radioactivity. And so things like uranium, thorium, other elements will turn into other things at very known rates. These rates of decay are very well measured. And we talk about it in terms of half-life, how long it takes for half of the substance to decay away from its original substance. For certain isotopes, for the isotope for plutonium-238, the half-life is 88 years. It's an artificial one we have to make in the laboratory by bombarding uranium with neutrons and use it to power things that go to Pluto. It's a nuclear power source. And so after 88 years, half of it will have decayed away. After another 88 years, half of that will have decayed away, and it goes down by power. So based on how well we know these things decay, if we can measure, like in an hourglass, if you can measure how much sand accumulates in the bottom, and you know how fast it's falling, you can infer how old it is. And that's especially true if one rock has multiple hourglasses of different sizes in it. This gets really hairy really fast. But suffice it to say, by measuring very accurately the ratios of parent isotope to daughter isotope, and knowing how fast this occurs, you can very accurately work out how old something is. And this has only been a technique that's been around since the late 1800s. Prior to that, we had no idea how old anything was. And is that what I want to say about that? Okay, so yeah, I think that's what I'll say about that. Probably a lot of you have heard of carbon dating, carbon-14 dating. It's a similar idea, but it's only useful for things that used to be alive. So you can't do carbon dating on rocks. You have to do something more clever, like potassium argon, or thorium, or uranium lead, or lead dating, or samarium neodymium. We do that a lot for moon rocks. That's how we know how old moon rocks are. They're typically between 3 and 4 billion years old. We do samarium, neodymium, radioisotope age dating on them and know how old they are. Now, combining those age dates with a lot of detailed mapping that's gone on the ground on Earth, we've worked out that Earth hasn't always looked the same. There have been various cycles of supercontinents in Earth's past where you get a large continent, a huge continent on one side of Earth. It breaks apart into continents that we have today, scattered across the globe, and then they'll reform, forming another supercontinent. Then they'll break up again, and then they'll come together again. And this cycle has probably happened 3 or 4 times in Earth's 4.5 billion year old history. And we know that 4.5 billion years from age-dating meteorites. And so one of the ways we know this, that it happened, and not just how long it took to happen, is partly from looking at fossils that occur in very well correlated regions across different continents. So we have confidence that South America and Africa used to be joined together, not just because their coastlines fit together rather well, but also because certain fossils, like this guy, they're only found in this part of South America and in this part of Africa. And if they're ever joined together, as their coastlines suggest, then this patch also matches up. Same thing can be done across Africa and India, even Antarctica. Antarctica used to be much closer to the equator. And so we see fossils in Antarctica of tropical species. And it's not actually their coastlines that we match up, it's actually the boundaries of their tectonic plates, which may or may not reflect the current coastline based on current sea levels. So that's very clever. This has also been done not just with fossils, but by tracking mountain ranges that appear to move across each other. For instance, yeah, this is perfect. So the Andes, is it the Andes here? The Andes Mountains actually go underneath the kind of Pacific Atlantic boundary there, and they become the Trans-Antarctic Mountain Range. It's the same mountain range. It's the same rocks. It's the same process that formed those rocks. The same thing is also true in eastern Canada, the Maritime provinces, and Scotland. Those were combined. They have the same geologic units, the same mountain ranges. So this is just some of the evidence that Earth has undergone a phase change. Here's, this is a painfully slow animated GIF of the continent separating from the most recent time this happened, we call it Pangea. There were several other times before then, like Rodinia and Gondwanaland. But the continents drift apart, and that's driven by seafloor spreading that we can watch happening now on like the Mid-Atlantic Rift. in the middle of the Atlantic Ocean. You can actually go down there with a submersible, and you can sometimes see magmatic eruptions. You can monitor earthquakes that happen here, which can then lead to tsunamis. And you can see where the floor of the Atlantic Ocean is growing apart. Now, while the Atlantic Ocean is growing, the Pacific Ocean is shrinking by approximately the same amount. And it's a process called subduction. And this is happening off the coast of Asia. This is actually what Japan is it's a volcanic range from the Pacific plate diving underneath the Asian plate. And as the Asian plate goes down, it starts to melt. And actually what it does is it releases water into the overlying crust here. The water makes it easier to melt, and that causes volcanoes here. And if you've got an ocean right there, and you've got a volcanic island right there, that's what Japan is. That's what the Aleutian Islands of Hawaii are. So Earth's surface is highly mobile, is the takeaway. And it's happened, this has been going on, we don't know exactly when plate tectonics started. It was probably at least 3 billion years. It's probably been going on for about 3 billion years or more. Here's what that looks like. This is the Mid-Atlantic Rift. There's no magmatic activity here right now, but you can see where the crust has been buckled and faulted. And it's just a lot of basalt, which is on the table. Sometimes we do see magmatic eruptions going on. National Geographic has been really good about photographing some of this stuff. A lot of just crazy stuff going on in the ocean floor. So we're at almost an hour. If you have to go, that's fine.
No, I just have to go because my granddaughter has a basketball game.
I'd
rather be here.
This is the Mid-Atlantic Rift. This is one of the few places where it's above sea level. This is in Iceland. And I've never been to Iceland. Anyone here been to Iceland? No? The sun. Everyone's going to Iceland now because their economy tanked and tourism is great. So, but you can actually walk through the middle of where two tectonic plates are in the process of rifting apart. Right there, right there, where that guy is. That's it. Those are two tectonic plates. One's Europe and one's America. And they're moving apart. And it's one of the few places, like I said, where that's actually above sea level, where that happens. So, Job tells us to do science, but ask the animals and they will teach you, or the birds of the sky and they will tell you, or speak to the earth, geology, and it will teach you, or let the fish of the sea inform you. Which of these does not know that the hand of the Lord has done this? Psalm 104, which has lots of great creation-related passages in it. May the glory of the Lord endure forever. May the Lord rejoice in his works. He who looks at the earth and it trembles, who touches the mountains and they smoke. He set the earth on its foundations. It can never be moved. You covered it with the watery depths as with a garment. The waters stood above the mountains. But at your rebuke, the waters fled. At the sound of your thunder, they took to flight. They flowed over the mountains. They went down to the valleys, to the place you assigned for them. You set a boundary they cannot cross. Never again will they cover the earth. Really quick here. Stratigraphy is the science of layered rocks. And it's, while we can't, without radiometric age dating, we can't get precisely how old they are, but we can get a sense of their relative age simply by realizing that the lower down rocks, if they're sedimentary rocks, were laid down first and they're oldest, and the younger stuff has been subsequently laid up on top. I took this picture in South Dakota. And you can see fossils down there that are different from different periods of different geologic units. You can see some of this is lithified, it's turned to stone sand dunes. Some of it's like beach sand, some of it's more like coral reef. And so the environments have changed over time. And this is analogous to looking at distant starlight and seeing back in time. Although we're not literally looking back in time now, but we're seeing the effects of past things in time. So it's analogous but not identical to looking at fossilized starlight. Just more layers of stratigraphy here. I took this picture also in South Dakota. These are weathered volcanic eruptions, ash. Meteor crater in Arizona. You can see layers of stratigraphy here. When the asteroid hit 55,000 years ago, it penetrated down through various layers of rock. And so they're like a natural drill, asteroids are. And so you can see different layers of exposed rocks. And you can see different ages of rock units as you go down there. I took this picture of the rim of the Grand Canyon at sunset. There's 1 billion years of geologic history exposed right there in those rocks. As you go from the top of the Colorado Plateau down to the Colorado River, that's the equivalent of 1 billion years worth of time.
What would the effect on the world that we know of be of an asteroid strike like that?
It depends how big it was. Last week, the Atlantic Ocean got hit by
that one in particular.
So meteor crater, this one right here?
Yeah.
There'd be like a nuclear explosion going off in the city.
So it's not, it impacts that general area, it's not.
Right, it'd be a regional effect. If it got much bigger than that, it would be global. It would send up an ash cloud that would
Cover the
area. Yeah,
How big was that asteroid, like in relative terms?
about the size of the screen.
What?
Really?
Yeah,
That?
It's just,
Yeah.
he's just moving that fast.
it's moving at like 50
Holy
50
smokes.
kilometers per second.
So if something the size of this church hit the Earth, we'd be nuclear clouded and all that.
I don't know if it'd be a global catastrophe, but it would be getting close. It'd be regionally catastrophic.
Does it knock the Earth off its orbit?
Nope.
Wow.
That's
I mean,
unbelievable.
Earth has a big bulk. We've got a lot of momentum, and so we can get hit around quite a bit without changing our orbit or our tilt, which would affect seasons.
You said something hit the Atlantic Ocean?
Yeah, a couple weeks ago. If it was a few miles, 100 miles to the west, Rio de Janeiro would be a hole in the ground. This happened last week, and an asteroid hit the Atlantic Ocean.
How
Yeah,
often do we get hit?
a few times a year.
Really?
Most of them happen in the ocean, or Antarctica, or Siberia, or most people live along the coast.
Just by dumb luck.
Yeah,
Yeah.
yeah.
Holy smokes.
Day before Valentine's Day 2013, I should have put a video in here. Man, the Chelyabinsk, the city of Chelyabinsk,
Yes.
Russia,
Yeah.
was hit by an asteroid.
But it was well documented on
Yeah.
video cams.
Right. Yeah, and you can see this stream coming. If you stick around after, I'll show you the video. It's just coming in. You can see it from people's dashboard cameras, which they have an insurance incentive to have. And you see this incandescent trail coming through the sky, billowing smoke behind it. And then you see it fragmented into a bunch of smaller pieces. And the people get out of their cars, are looking around, and then the shockwave from it hits. And that shockwave blew in windows, and about 1,000 people had to go to the hospital for laceration wounds. And then part of it actually survived and made a hole in a frozen lake. And they went down and drug up part of it. So,
The ones that fall in the ocean create tsunamis?
small ones. I think they were ganked out by the time they got to the shore.
Well, didn't one hit the Chesapeake Bay?
A few million years ago, about 30 million years ago. Yeah, at the mouth of the Chesapeake Bay, there's an impact crater that's been filled in with mud, but you can see it in geophysical surveys. There's an impact crater there that would have inundated much of the East Coast with a tsunami.
So we're just incredibly lucky.
Yeah.
Or,
I mean,
or
if something the size of that screen hits in the middle of New York City's toast.
Yeah.
Jesus, that's unbelievable.
Thank you, God.
Jesus,
Yeah, so NASA actually is spending money on how to deflect asteroids. Not as much as I think they should be, but they are spending some money on
They're
it.
called Bruce Willis, right?
It's called the Asteroid Redirect Mission. It's a $2 billion spacecraft.
Do people know that they're like, do they know they're coming?
Not all the time, that's the scary part.
You can't really
The
track
small ones are hard to find.
It's not like you can like it's gonna hit, like you can't stop it.
If we had a several years warning, we could possibly stop it.
Okay.
But the small ones, like that just hit the Atlantic, weren't discovered before they hit. So we actually need space surveillance telescopes to get above the atmosphere. A lot of them come from the direction of the sun, which means they're hard to look at because it's the sun that looks at things. And so they're coming at you from the daylight side, which is hard to do astronomy in the daytime. And they're small, so they're dim. And so it's a problem. What we actually need, this is kind of off topic, but what we need is an infrared telescope at Venus's orbit looking back at Earth's orbit. And that would allow us to more adequately categorize them. So the moon, moving on, stratigraphy. The moon also has stratigraphy. Here's the horizon in the distance. This is the Apollo 15 landing site. Dave Scott or Jim Irwin took this picture. You can see some exposed lava flows in the wall of a lava channel. This is called a rill. We're seeing the wall of a, kind of like a canyon. It's like a carved valley from lava. You can see some of the stratigraphy there. The stuff on the bottom is older. You can see some of the stratigraphy blown up in the bottom inset there. That's the Hadley Apennine Mountains on the moon. How many people saw the moon this morning in the sky? Anyone else besides me? Pluto also has stratigraphy. This was taken this past July, because prior to July we had no idea what Pluto looked like. Where the asteroids that form these craters have excavated to different stratigraphic depths here. And you can see these dark layers within some of these craters. This crater floor is all dark, but you can actually correlate these probably. You can come up with a stratigraphic column whereby you can say that this dark rim of stratigraphy here probably correlates with probably this one over here. There's like a continuous dark geologic unit that goes under all of these, and these craters punch into that to different depths, revealing different amounts of it. There's ejecta spewed out of this crater that's dark material from the middle there, so we can get a sense of what's inside rather than what's been thrown on top. This is where I was last Sunday, not here. This is just a volcanic cinder cone in the Mojave Desert of California. That's me on a dry lake bed that's been dried up for several thousand years. This is my friend Lori on another dry lake bed that's all salt encrusted. If you're in the area next Friday at the Space Telescope Science Institute on the campus of Johns Hopkins University, she's giving a talk on her work on astrobiology and the origins of life.
Wow.
It's at noon next Friday at the Space Telescope Science Institute. It's free. Pluto, it's just pretty. The stuff on the right is a nitrogen ice glacier. The stuff on the left are water ice mountains, 10,000 feet tall. You can see different layers of atmospheric haze above there. Pluto's atmosphere is...
What's that little point of bright white on the left?
What? Here?
Yeah.
Not just valley fill ice. I don't know. These are all mountains, and that's just a valley in between. Yes. It's probably methane frost. Mars is gorgeous. This is the largest volcano in the solar system, Olympus Mons. It's not that old in geologic terms, maybe 1 billion years old. This is the same type of volcano as Hawaii is. It just kind of spews ketchup-y lava and just kind of flows down, forms a very broad base. This is the size of Arizona in width. And there's 3 other large volcanoes there too. I love these shots. This is from the European Space Agency spacecraft Mars Express. And it's in a very elliptical orbit. And on the high points of its orbit, it can take these really broad sweeping panoramas and they're gorgeous. Here's the North Pole of Mars. This polar ice cap. It's surrounded by dark sand dune fields of like Hawaiian black sand. I don't really have anything besides this is gorgeous. Praise God. This is Saturn's moon Enceladus with Saturn as a backdrop. Enceladus has constant geysers going off on its south pole of water ice that are going so fast, and Enceladus' gravity is so weak that it just escapes the moon and goes in orbit around Saturn. And Enceladus is a good candidate to look for signs of life because it has a liquid water ocean underneath its solid icy crust. The thing is that Enceladus' geysers could not have been going off for the age of the solar system. They probably turned on and off based on different geologic events. So also Enceladus doesn't have enough, we don't think it has enough internal energy to have been active for 4.5 billion years. So it's probably only active episodically. This is the surface of a comet taken by the European Rosetta spacecraft. We're just looking at a cliff of water ice, basically, and dirt. And part of the spacecraft is on the upper left. And then Earth is seen from beyond the moon, from the Chinese Chang'e 5T spacecraft, taken only 2 years ago. And then this was taken by one of our spacecraft. That's the Earth rising above a crater on the moon. You can see we're looking inside of a crater. Here's a central mountain in the crater. There's cooled lava that's been cracked on the floor of this crater rim, lots of faulting and kind of the stair-step terrace morphology of the Earth rising.
What's the brown area of Earth?
This is Africa. This is Sahara. There's Saudi Arabia.
I love it all seen through lace curtains.
Oh. Well, maybe I should maybe design my PowerPoints in the future.
That is great.
Oh, and then how the moon formed. The moon, based on our analysis of moon rocks, and our understanding of orbital mechanics, the most likely scenario that makes sense of all that separate stuff is the fact that Earth probably got hit by a Mars-sized planet when Earth was only about 30 million years old. And so something hit, it splashed off lots of material that went into orbit around Earth. The self-gravity of those bits of ejecta recoalesced to form the moon. I don't know if I have a movie on that. No, I don't. This again inspires me to the Psalms. Great are the works of the Lord. They are pondered by all who delight in them. I think that's a repeat. How many are your works, O Lord? In wisdom you made them all. May the glory of the Lord endure forever. May the Lord rejoice in his works. He who looks at the earth and it trembles. Sorry, that's a rerun. But again, I am moved personally, emotionally, and spiritually, and my capacity, speaking personally, I feel is enhanced to worship God just by finding out what there is to know about the universe. And if we didn't know these things, if we didn't invest in doing science, either as a society or as individuals, we wouldn't be able to praise God for these sorts of things. Our ability to worship would be stunted. So my epilogue is, and God saw all that he had made, and it was very good.